Today's lecture is about factorial analysis of variance or FANOVA. Before I start explaining FANOVA, let us see what is simple analysis of variance or ANOVA. Analysis of variance. What is analysis of variance? So first of all, what is analysis of variance? Denoted by ANOVA. In ANOVA there is only single factor, also called as treatment. The object of analysis of variance is to partition the total variance in the data set into variance due to treatments and variance due to error. So total variance is partitioned into variance due to treatment plus variance due to error, also called as error variance. So total variance is partitioned into variance due to treatments and variance due to error. In the simple analysis of variance. In the factorial analysis of variance, there are different factors. So factors can be, for example, you can have two factors. Two factors, call them factor A and factor B. Factor B. So there are two factors. Now I am explaining FANOVA, factorial analysis of variance. That should have at least two different factors. For example, factor A and factor B. In the case of epidemiology, these can be, factor A can be exposure to a certain disease or to a certain stress condition, exposure, for example, to X-rays. So there can be mild cases, number one, mild, number two, high exposure. Mild and high exposure. These are two levels of exposure. Two levels. Two levels of exposure. Number two, treatment A or drug A. Drug A, treatment B. The patients are exposed to two different types of treatments. So now we have two factors, factor 1 and factor A and factor B. So if we partition the total variance, then we will have to partition it variance due to VR, I will write down in short VR, variance due to factor A, plus variance due to factor B plus variance due to interaction of A and B. Often the factors interact with one another, so we also need the variance of interaction. A and B is interaction. Plus variance due to error. So the total variance here is partitioned into variance due to factor A plus variance due to factor B plus variance due to factor A into B plus variance due to error. Similarly, if we have three factors, A, B, C, three factors. For example, this is a field experiment on crop growth. A can be kind of fertilizers, B can be kind of irrigation, and C can be varieties of the crop. So there are three factors, A, B, C. How to partition this? Total variance, we always partition the total variance into variance due to different factors. Variance due to factor A plus variance due to factor B plus variance due to factor C plus variance due to interaction of A and B, A into B plus interaction of variance of A into C plus variance of interaction of B and C, B into C, plus variance due to error. There will always be variance due to error. Why there is error? Error is due to genetic variability among the subjects. For example, human beings or plants, they have genetic variability. So each one is slightly different. For example, in human being, there are different height, different color, different shape of nose, different hair type, and so on. So there is variation can be due to genetic variance. It can be due to experimental technique or method that we use. So there is slight variation between each method, and then the error can be due to measurement error. Measurement. The instruments that we use are not 100% accurate. So measurement error, there is error in measurement. So these are the causes of error. So there will always be an error term. In all the statistical models, there will be an error term. So here there is error, here in the first case also there is error. So in any analysis of variance, whether simple analysis of variance or factorial analysis of variance, there will always be some error. This is the reason for analyzing the data. If there is no error, then really there is no need for analysis. There is always some error which creeps into the experiment, and therefore we have to separate out the variance. Separate out the variance for error and variance due to different causes that we want to know. Right? On replicates, Suppose we are testing the effect of control, that is no treatment, and SO2 and NO2, sulfur dioxide, nitrogen peroxide, on the growth of plants. And the values are 10, 10, 12, 12, height in centimeters, 8, 8, 9, 3, 5, 5, 6, 3. Suppose these are our plants, 12 plants. Take the picture. The 4 plants actually, 4 replicates. Now we will have to assign treatments to these. The treatments are assigned randomly to the experimental units. Each of this is experimental unit. The treatments will be assigned using random numbers. Random numbers can be generated from the calculator. There is an RAN function, RAN number function in calculator. First you press shift, then RAN number, and then equal to. This is actually second function where there is a dot, and the second function is RAN. So you press shift, then dot, then equal to. That gives you on the screen a random number. Using those random numbers, we assign the treatments. And these are the 3 treatments: control, sulfur dioxide, and nitrogen peroxide. So K is equal to 3. Right? Now we can analyze this data into analysis of variance and form an ANOVA table in which the first column is source. In the source there is treatment. The variation can be due to treatments, and number 2 due to error. And this is the total variance. Total. So in this case, sum of squares SS, degrees of freedom df, then ms, mean square, and then finally the F ratio, which is most important. F ratio. F is most important. Degrees of freedom will be 2 and 9. If we have 3 treatments, so k is equal to 3, degrees of freedom for treatment will be k minus 1. So 3 minus 1 is equal to 2. And this degrees of freedom is n minus k. Total number of observations, total number of observations minus k. So total observations are 12 minus 3 is equal to 9, and this will be 11. Sorry, this is 9, this is 11. And then divide the sum of squares by degrees of freedom. So that gives us 37.33 and 3 point. You can check it yourself and get the right numbers. Mean square is equal to sum of squares divided by degrees of freedom. So this is sum of squares SS divided by degrees of freedom, 74.66 divided by 2, 37.33, 28 divided by 9, 3.1. So these are the mean square, and this is the F ratio. F ratio is simply mean square of treatment divided by mean square of error. So 37.33. So finally we get the F ratio. This is the main statistic that we check in the F table. There are tables for checking the F value, and in that degrees of freedom is given in 2 directions. df1, which is for treatment, and df2, which is for error. Degrees of freedom 1 is for treatment, so that is degrees of freedom 1, df1, and df2 is for error. So this is 2 here, this is 9. So 2 against 9, we check the value of F in the F table. This value is larger than the F value in the table. Take my word for it, I don't have the table right now. But this value is much larger, therefore it is significant. In other words, there is a significant effect of treatment. There is significant effect of treatments which are sulfur dioxide and nitrogen peroxide on the plant growth. The values are actually height of plants in centimeters. So the average value is much higher. Average value is much higher for the control which is not treated. Average value is 11, right?